Now today we start a new topic, maxima and minima. So see here, definition of maxima of a function f of x. So see here, a function f of x is said to have a maxima at x equals to c if the value of the function at x equals to c is greater than any other value of f of x in delta neighborhood of c. So here we denote the delta neighborhood by the open interval c minus delta c plus delta. So see the meaning of this definition, that is, for a small delta greater than 0 and for x belongs to open interval c minus delta c plus delta, we have f of c greater than f of x. The value of f of c is called a maxima of f of x. That means here we consider a point x equals to c. For that value, that function f of c is greater than f of x, and this x belongs to c minus delta c plus delta. Thus the function f of x will have maxima at x equals to c if f of x is increasing in c minus delta less than x less than c and decreasing in c less than x less than c plus delta. So in previous lecture we already discussed increasing and decreasing function. So with the help of increasing and decreasing function, we can also define maxima of function f of x as the function f of x will have maxima at x equals to c if f of x is increasing in c minus delta less than x less than c and decreasing in c less than x less than c plus delta. That means for increasing function, we consider here this lower limit of this open interval, that is c minus delta less than x less than c, and for decreasing function we consider this upper limit c plus delta. So right here c less than x less than c plus delta. The next definition, maxima of a function f of x. A function f of x is said to have minima at x equals to c if the value of function at x equals to c is less than any other value of f of x in the delta neighborhood of c. Now we comparatively discuss the maxima of a function and minima of a function. See here, in definition of maxima of a function at x equals to c, the value of f of x is greater than any other value of f of x in a delta neighborhood of c. But in minima of a function, here see, the value of f of x, value of function at x equals to c is less than any other value of f of x in a delta neighborhood of c. That means in maxima, the f of x at x equals to c has greater value for any other value of x belonging to delta neighborhood of c, and in minima of function, the value of f of x at x equals to c is less than any other value of x belongs to delta neighborhood of c. Then see here, that is for small delta greater than 0 and for x belongs to c minus delta c plus delta, we have f of c less than f of x. Here we write f of c greater than f of x for maxima, and for minima we write f of c less than f of x. The value of f of c is called a minima of f of x. Thus, the function f of x will have minima at x equals to c if f of x is decreasing in c minus delta less than x less than c and decreasing in c less than x less than c plus delta. So here in definition of maxima, here f of x is increasing in c minus delta less than x less than c. Here in minima, the f of x is instead of increasing, here function is decreasing in c minus delta less than x less than c, and here in maxima the function is decreasing in c less than x less than c plus delta, but in maxima the function is increasing in c less than x less than c plus delta. So you remember any one definition, from that you can remember the other definition. If f dash of c equals to 0, then at x equals to c the function is neither increasing nor decreasing. That means if we find the value of f dash of x at x equals to c and that f dash of c becomes 0, then the function is neither increasing nor decreasing. Such a point on the curve is called turning point or stationary point of the function. So this point is called stationary point, where the derivative of that function is 0. That means the function is neither increasing nor decreasing. That point we call turning point or stationary point. Any point at which the tangent to the graph is horizontal is a turning point. So we know that the slope of a line parallel to x-axis is 0. That is, in derivative form we say dy by dx equals to 0. So here we can locate the turn point by looking for point at which dy by dx equals to 0. That means slope of tangent to the given curve is 0. That means that tangent is parallel to the x-axis. So see here, at these points if the function has maxima or minima, then these are called extreme value of the functions. So this concept will be clear when we solve the problem from the exercise 2.4. To find the extreme value of the function, let us use following test. So we have used test for extreme values of the function. To find the extreme values of the function, so first test is first derivative test. So in this way, with the help of first derivative, we find the extreme point. So see here, a function f of x has a maxima at x equals to c if number 1 f dash of c equals to 0, number 2 f dash of c minus h greater than 0, that is f of x is increasing for value of x less than c, and number 3 f dash of c plus h less than 0, that is f of x is decreasing for value of x greater than c, where h is a small positive number. That means if these three conditions are satisfied, then we say the function f of x has maxima at x equals to c, which is first condition. The derivative of function at x equals to c is 0, and for lower limit f dash of c minus h greater than 0, and for upper limit f dash of c plus h less than 0. Then second, a function f of x has a minima at x equals to c if number 1 f dash of c equals to 0, f dash of c minus h less than 0, that is f of x is decreasing for all values of x less than c, and number 3 f dash of c plus h greater than 0, that is f of x is increasing for value of x greater than c, where h is a small positive number. So for avoiding confusion, remember any one condition. So try to remember the first condition. Here f dash of c equals to 0 common in both. So we remember these two only, f dash of c minus h greater than 0 and f dash of c plus h less than 0, and we know that if f dash of x greater than 0 then the function is increasing, and if f dash of x less than 0 then the function is decreasing. So here c minus h for increasing and c plus h for decreasing, you have to remember in this way. Then second derivative test. Mostly for solving the problem we use this second derivative test. So see here, a function f of x has maxima at x equals to c if f dash of c equals to 0 and f double dash of c less than 0. That means here we have to check only these two conditions for the maxima or minima of a function at a given point. A function f of x has minima at x equals to c if f dash of c equals to 0 and f double dash of c greater than 0. That means why we call this test as second derivative test, because we find second order derivative. From first order derivative we find the extreme points, and with the help of second derivative test, for that extreme point we check whether the given function is increasing or decreasing. If f double dash of c equals to 0, then second derivative test fails, so you may try first derivative test. That means when second derivative test fails, we try to find the extreme point, first derivative test. Now see, concept will be clear with the help of this first example. Find the maximum and minimum value of f of x equals to x cube minus 3x square minus 24x plus 5. So we solve this example with the help of second derivative test. So see how to solve the problem to find the maximum and minimum value of given function. So see here, in solution first we write the given function. So here we write in solution f of x equals to x cube minus 3x square minus 24x plus 5, and we denote this f of x as equation number 1. Now we have to find first derivative, so we differentiate this given function with respect to x. So right here differentiate 1 with respect to x. Now we know that derivative of x cube is 3x square, derivative of 3x square is minus 6x, and derivative of minus 24x is minus 24. So we write here derivative of f of x as f dash of x, derivative of x cube as 3x square, derivative of minus 3x square as minus 6x, and derivative of minus 24x as minus 24, and derivative of 5 is 0. So see how to write the derivative. Derivative of x cube we know 3x square, derivative of x square which is twice x, so we write here twice x into minus 3, so we write here minus 6x. Then derivative of x with respect to x is 1, so 24 into 1 we get 24, here sign is minus, so write minus 24. So first we find first order derivative and we denote this as equation number second. For extreme value we equate this f dash of x with 0, so right here f dash of x equals to 0. So here f dash of x means 3x square minus 6x minus 24, so we equate 3x square minus 6x minus 24 with 0. Now this is quadratic equation, so we take here 3 common, so write in bracket x square minus 2x minus 8. We know that product is 0 when both the value are 0 or any one value is 0. So here 3 is not 0, so the bracket we equate with 0. So right, that is x square minus 2x minus 8 equals to 0. Now we have to factorize this quadratic form. So here x square coefficient is 1, so we directly factorize this minus 8. So we write here x plus 2 into x minus 4 as the factor of this quadratic form. So from this we write x is equals to 2, x equals to 4. So first we write x plus 2 equals to 0 or x minus 4 equals to 0. So from this you can write x equals to minus 2 and x is equals to 4. Now these are the extreme point. So right here you can say stationary points also. These stationary points are x equals to minus 2 and x equals to 4. So we first find the second derivative. So right here differentiate a second with respect to x. So from this first derivative we find a second derivative. So for that we have to differentiate this second. So differentiate this equation second with respect to x. So here derivative of 3x square we get 6x and derivative of this minus 6x we get minus 6, and this 24 is single constant, so its derivative is 0. So we get f double dash of x from this second equation as 6x minus 6. Now we have to check for x equals to minus 2. So from equation 3 we get, so substitute x as minus 2. So we write here f double dash of minus 2 equals to 6 into minus 2 minus 6 as it is. So minus 6 into 2 we get minus 12, minus 12 minus 6 we write minus 18, and minus 18 is less than 0. That means this f double dash of minus 2 is less than 0. That means the function is increasing. So we write here at x equals to minus 2 f of x has maximum value. For maxima of f of x, put x equals to minus 2 in equation 1. So from this second derivative we confirm whether the given function has maximum or minimum value. So here we get this f double dash of minus 2 less than 0. That means the given function has maximum value. So to calculate the maximum value we have to substitute x equals to minus 2 in given function, that is in equation 1. So for maxima of f of x, put x equals to minus 2 in equation number 1. So here we replace this x by minus 2, this x by minus 2 and this x by minus 2. So we write here f of minus 2 equals to minus 2 cube minus 3 into minus 2 square minus 24 into minus 2 plus 5. So here minus 2 cube we get plus 8. Here minus 2 square we get plus 4. So 2 cube is plus 8, and here plus 4 into minus 3, that is minus 12, and here minus minus plus 48 plus 5. After adding all these terms we get f of minus 2 as 33. Therefore the value of given function f of x maximum at x equals to minus 2 and value is 33. Now we check for x equals to 4. From equation 3rd we get, so first we write the equation number 3rd. So we substitute x equals to 4 here. So we get 6 into 4 minus 6. So here 24 minus 6, which we get 18, and 18 is greater than 0. That means this function is increasing. So this function has minimum. So we write here at x equals to 4 f of x has minimum value. Now we have to find the minimum value with the help of equation 1. So for minima of f of x, put x equals to 4 in equation number 1. So first we write equation 1 here. Now substitute this x as 4, this x as 4. So write here 4 cube minus 3 into 4 square minus 24 into 4 plus 5. So after calculating this we get f of 4 equals to minus 75. this is minimum value. Therefore local minima of f of x is 33 when x equals to 2, and therefore local maximum of f of x is 33 when x equals to 2, and local minimum of f of x is minus 75 when x equals to 4. So in this way we find maximum and minimum value with the help of second derivative test.